Hello friends, how are you? I hope you are doing well. Today in this video, I am going to explain thermal expansion. Children, whenever you are in a class, in a period of 40 minutes or 45 minutes, whenever I am taking more times, you are not feeling comfortable. The fact is that you have lot of energy. You can't sit within a limited space for more time. You want more freedom. So you want to move on the veranda, you want to go to the playground, you want to go to the bathroom, whatever it may be, because you have energy, you need some more space. So here also, in case of a thermal expansion, same things happen. In most of the cases, a substance expand on heating. I am not saying that all time a substance expand on heating, but maximum cases are there where the substance expand on heating. Some exceptions are there, no doubt. For example, in case of water, when the temperature of water we are increasing from 0 degree to 4 degree Celsius, within that temperature, increasing temperature, water is not increasing its volume. So this is the special case anomalous behavior of water, what we will discuss in the next period. Similarly, some other cases like silicons are there, where instead of increasing the temperature also volume does not increase, but maximum cases volume increases with increase in temperature. So I have written the heading thermal expansion. For example, a substance is there. In that, number of atoms, or you can say number of molecules are there. You think that now its temperature is 27 degrees Celsius. I shall supply the heat. I shall provide the energy. Definitely their kinetic energy will increase. As a result, they will try to move in here and there randomly. That means the molecular space will increase. The space between the molecules will increase. As a result, it will expand. So I said that in maximum cases, a substance expand on heating. So there is an exception I said, where we say that is the reverse expansion. In case of water or silicon I said, so that is the special cases what I shall explain in the next period. Today just will be restricted within the thermal expansion and coefficient of a thermal expansion. So maximum substance expand on heating. Substance expand on heating. But the thing is that this expansion can be classified into three types. One is linear expansion. Second one is superficial expansion. Third one is cubical expansion. So what is the linear expansion? Linear expansion means whenever we are supplying heat, a substance changes its dimension, no doubt at all. Length, breadth, height, everything will change. But the thing is that some cases are there where the expansion takes place in a particular dimension appears. That means, for example, this is a iron rod. You think that its length is 100 centimeter. Its radius is 1 centimeter. If I heat it will expand. Its length will increase. Its area of cross section also will increase. But if I compare the radius of this rod with this length, it is very less. That means the cases where the expansion appear along its length, that is called linear expansion. The expansion along its length. The expansion will take place from all sides. Whether it is the length, the breadth, the height does not matter. But the expansion appear along its length. That is called the linear expansion. So, suppose the length is L. The temperature is T. I increase the temperature. Now the temperature became T plus delta T. And length became length L plus delta L. How? Whenever we are supplying the heat, the space between the molecules are increasing. As a result, its dimension also changing. But in this case, if the length is more in comparison with the thickness, with the diameter or radius or area cross section, whatever it can be, the expansion appear along its length. That is called linear expansion. So I have, suppose it is 100 centimeter iron rod. Its radius is, length is 100 centimeter, radius is 1 centimeter. For example, after heating, its length increased 1%. 1% means it will become 101 centimeter. What about the radius? Radius also 1% will increase. That means 1 plus 0.01 means 1.01 centimeter. Radius increased, length increased, but the expansion appear along its length because length is comparatively more than its other dimensions. So I can say that this type of expansion is called linear expansion. So if the expansion takes place along its length, that is called the linear expansion. So this is the original length L. Suppose L is the original length. After heating, its length became this one, or you can say delta L increased, or I can say this is L plus delta L. Here was the temperature T. Now the temperature became T plus delta T. The substance expanded along its length, that is called linear expansion. This linear expansion, or I can say that this change in length directly proportional to change in temperature. Delta L directly proportional to delta T. Because when we are supplying more heat, means temperature is increasing, length is increasing. So in place of this proportionality symbol, okay, or I can say that this delta L by L directly proportional to delta T. Original length change in length per original length. Change in length divided by original length is directly proportional to delta T. Suppose we will remove this proportionality symbol, we will write equal to alpha into delta T. Okay, so I can say that this alpha is equal to delta L upon L into delta T. This alpha is called coefficient of linear expansion. This is coefficient of linear expansion. So I can say that it depends upon the material. Different material having different coefficient of expansion. So I can say coefficient coefficient of a linear expansion of a material. It may be iron, it may be copper, whatever it may be. So how can we define this? So I can write that the coefficient of linear expansion, the coefficient of linear expansion is defined as the change in length per unit original length per unit change in temperature. So I have written that this alpha is equal to delta L upon L into delta T, whereas the delta L stands for change in length, L is the original length, delta T is the change in temperature. So this is the about the coefficient of a linear expansion. Alpha is equal to del L upon L into delta T. Similarly, now suppose a metallic plate is there. A metallic plate is there. Okay, this very thin. You think that its area is A, temperature is T. When we supply the heat, suppose its temperature became T plus delta T, that time it became A plus delta A. What happened? Here the expansion appeared along its area. The expansion takes place along its length, breadth and height, no doubt at all. But the length and breadth is comparable with the thickness or height. So the expansion appeared along its area. So the expansion along its area, we say area expansion or superficial expansion. Area, or we can say superficial expansion. So like the previous case, I can say that this change in area per unit area, change in area per unit area directly proportional to change in temperature, or I can write that delta A upon A is equal to beta into delta T, where beta is equal to delta A upon A into delta T. This beta is called coefficient of area, or you can say superficial expansion, because here expansion appear along its area. So this is called the coefficient of superficial expansion. You can say that change in area per unit original area per unit degree in temperature, means what degree Celsius change in temperature or what Kelvin change in temperature also we can say. So this is about the coefficient of a superficial expansion. Beta is equal to delta A upon A into delta T. So the third type expansion means cubical expansion. Cubical expansion, or we can say this is associated with the volume expansion. For example, one cube is there. T, its volume is V. Whenever we are increasing the temperature, the molecular space increasing, as a result, the volume also increasing. It became V plus delta V, temperature became T plus delta T. This type of expansion is called cubical expansion or volume expansion. So here length, breadth and height, all three are comparable. So the expansion takes place and also appear along its volume. This type of expansion is said to be cubical expansion or volume expansion. So I can say that this change in volume directly proportional to change in temperature, or delta V upon V means change in volume per unit volume is directly proportional to change in temperature, or I can write delta V upon V equal to gamma into delta T. That means this gamma is equal to delta V upon V into delta T. That means coefficient of cubical expansion is defined as the ratio of change in volume per original unit volume per unit change in temperature. So I have denoted it by the letter gamma, that is equal to delta V upon V into delta T. So this is about the coefficient of expansion, or I can say coefficient of expansion of a material. So different substance having different coefficient of expansion. Okay, so you can say this is the rate of expansion, the rate of speed, how it is expanding due to increasing in temperature. So I can say it is the rate of expansion. If the expansion along its length, linear expansion, along its area, superficial expansion, along its volume, that is cubical expansion. So children, there is a wonderful relationship between these three, alpha, beta and gamma. So children, I hope that you might have subscribed this video, because if you want to continue your study systematic manner, definitely if my video you are liking, I hope that you will subscribe it. At the same time, you have to share this video with your friends. As a result, they can also take the benefit. Okay children, see here. So what is that wonderful relationship between alpha, beta and gamma? We will see that. So the relation we have to prove that beta is equal to 2 times of alpha and gamma is equal to 3 times of alpha. Just I shall try to explain you. Listen carefully. So a relation between alpha, beta and gamma. Listen carefully. This is the metal rod. Temperature T, length is L. After expansion, means when the temperature T plus delta T, it became L plus delta L. Now you see that suppose the temperature is T, area is A. Now we supply the heat, its temperature increased from T to T plus delta T, and the area became A plus delta A. Listen carefully. So I am going to establish a relationship between alpha, beta and gamma. Okay? Now let us come back. So I said that this delta L upon L is equal to alpha into delta T, or I can say that this delta L is equal to L into alpha into delta t. So in this case, for example, in the first case, length is L, breadth is B. After expansion, its length became L plus delta L and its breadth became B plus delta B. For example, okay, I have taken its length is L, breadth is B. Here after expansion, L plus delta L, B plus delta B. So now delta L is equal to L into alpha into delta T, implies that this L plus delta L is equal to L plus L alpha delta T. I can take L common. This is 1 plus alpha into delta T. Listen carefully. This is about the L plus delta L. Similarly, I can also write B plus delta B. This is also length. This is breadth also. That is also length. Okay. So I can write that B plus delta B is equal to B plus B into alpha into delta T. This is equal to B into 1 plus alpha into delta T. Listen carefully. So children, this is about the length and breadth of the expanded substances. Before that it was L and B. Now it became L plus delta L and B plus delta B. Now if I want to find the area, this area is equal to or A plus delta L. A plus delta L. So this is the expanded area. It is the product of expanded length and expanded breadth. So I can write L plus delta L into L of 1 plus alpha into delta T I mentioned here. Breadth into 1 plus alpha into delta T. So I can write that LB into 1 plus alpha delta T square. So this is equal to LB of A plus B whole square. So I can write 1 plus alpha square delta T square plus 2 alpha delta T. Listen carefully. Alpha is the coefficient term. So the coefficient term is very small. If it is very small, if I take its square also will be very small. For example, 0.1. You are taking its square, it is becoming 0.01. Again it is decreasing. So this alpha square delta T square can be neglected. So in place of L into B, that is the area of this small object. So I can write A 1 plus 2 alpha into delta T. Listen carefully. So this one I can write A plus 2A alpha into delta T. So this A cancel. Then what is left? Delta A is equal to 2A alpha into delta T. Implies that delta A upon A into delta T is equal to 2 alpha. So already I said that this delta A upon A into delta T, this is coefficient of a superficial expansion beta, implies that this beta is equal to 2 alpha. Got one relation? Beta is equal to 2 alpha. First relation we established between coefficient of a linear expansion and coefficient of a superficial expansion. Okay, here alpha for the linear expansion, beta for the superficial expansion. So one more relation we will see it, that is related with the volume. Now, suppose one solid substance is there. Now the temperature is T. Okay. Now, its volume is V. This is length, this is breadth, this is height. After expansion, suppose its volume increased. Now the temperature became T plus delta T, volume became V plus delta V. That means say this length became L plus delta L, this is B plus delta V, this is H plus delta H. Okay, so now what will be the new value? V plus delta V. We know that volume is equal to, volume formula what? Length into breadth into height. Length into breadth into height. This is the expanded volume. This is the expanded volume. So this is the expanded length plus expanded breadth plus expanded height. That means I can take this is L plus delta L into B plus delta B into H plus delta H. So I have taken that is length into breadth into height. So in this case, now previous case I said that L plus delta L, we wrote that L into 1 plus alpha into delta T. So again this is, so in this case we can write B into 1 plus alpha into delta T, H into 1 plus alpha into delta T. Okay, so I can write that A, B, H 1 plus alpha into delta T cube. 3 times are there, so I multiplied, it became cube. So see the children. So V plus delta V is equal to LBH. This is equal to V into 1 plus alpha into delta T cube. So I can write A cube plus B cube delta T 1 plus alpha into delta T cube. This is equal to V of 1 cube plus alpha cube delta T to the power cube, A cube plus B cube plus 3AB or 3 alpha into delta T of 1 plus alpha into delta T. This is equal to V into 1 plus alpha to the power 3 delta T to the power 3 plus 3 alpha delta T plus 3 alpha square delta T square. So here the coefficient of a linear expansion alpha is very small. So the alpha to the power 3 is given. So I can easily neglect it. Similarly, here also alpha square, which is very small. For example, you see in case of iron, the coefficient of coefficient of expansion of iron is very less. It is 1.2 into 10 to the power minus 5 per Kelvin. So we can neglect this alpha square because if the alpha is very small, if I take its square, it will be more small than previous. Same thing, if I take its cube, it will be more smaller than previous. So we can neglect it. So we can write that V of 1 plus 3 alpha into delta T. So this V we cancel. So I can write that, V of 1 plus 3 alpha into delta T is equal to V plus 3V alpha into delta T. Implies that this V cancel. So here left a delta V is equal to 3V alpha into delta T. Implies that delta V upon V into delta T is equal to 3 alpha. Implies that this gamma is equal to 3 alpha, because we know that coefficient of a cubical expansion is equal to ratio between change in volume per unit volume per unit change in temperature. So we got the next relation, which is the gamma is equal to 3 alpha. So already we proved this gamma is equal to 3 alpha. See. So we got the relation between alpha, beta and gamma. So here I can write alpha is equal to beta upon 2. This alpha equal to gamma upon 3. That means alpha upon 1 is equal to beta upon 2 is equal to gamma upon 3. That means alpha is to beta is to gamma is equal to 1 is to 2 is to 3. This is the beautiful relationship between alpha, beta and gamma. You see that suppose in case of iron, so its coefficient of expansion is 1.2 into 10 to the power minus 5 per Kelvin. Per Kelvin is the SI unit of a coefficient of expansion. So here in case of alpha 1.2, if it is the beta, I can say beta is 2 times of alpha. Beta is 2 times of alpha means that is 2.4 into 10 to the power minus 5 per Kelvin. Similarly, I can say that gamma is equal to 3.6 into 10 to the power minus 5 per Kelvin. This is the relationship between 3 coefficient of expansion, coefficient of linear expansion, superficial expansion and cubical expansion. So students, I hope that you might have understood this today's video. So next video remaining concept we'll discuss. Until then, bye. Thank you.